Now, in part 2, we are going to derive number of holes in the valence band of an intrinsic semiconductor. It is denoted by NH. So, in the intrinsic carrier concentration derivation, there are two parts. One is number of electrons in the conduction band and the number of holes in the valence band. Now we are in number of holes in the valence band expression. We are going to see the valence band now. The limits being minus infinity to EV and EF is the Fermi energy level. Let the temperature of the intrinsic semiconductor is at T Kelvin, that is above 0 Kelvin, the temperature of the intrinsic semiconductor is increased. Thereby electrons are moved from the valence band to the conduction band. Then holes have been created in the valence band. We are going to determine the general expression for how many number of holes are present in the valence band per unit volume of the intrinsic semiconductor. Let us consider the energy level E here, where the holes are present up to this level. Here we have electrons. Then EV minus E is the range of the energy level in which we are going to find the number of holes. Therefore, this is, for example, if I am going to take this as 1 electron volt and this as 0.8 electron volt, then EV minus E is equal to EV minus E is 0.2 electron volt. For simplicity or an example, I have considered this EV minus E as 0.2 electron volt. This depends on how much amount of thermal energy is consumed by the electrons to cross the forbidden energy gap and to be available in the conduction band. So generally we can consider EV minus E as X kBT. Here we are going to consider the Fermi distribution function as 1 minus f of E, where f of E is the probability function for finding the electrons occupying a particular energy level. 1 minus f of E denotes finding the number of holes occupying the particular energy level. Here energy range is considered as EV minus E, which is equal to X kBT. Now we are going to find the number of holes in the valence band per unit volume of the intrinsic semiconductor. NH is equal to, now the general formula is Z of E dE, the probability function is 1 minus f of E. This is the density of states and this is the Fermi distribution function, the probability of finding holes in the valence band. The limit of the valence band is minus infinity to EV. For writing the limit, minus infinity to EV. Now substituting Z of E dE as here, NH is equal to integral minus infinity to EV pi by 2 8 mH, the effective mass of the hole is considered here, by h square, the whole power 3 by 2 e power half dE and 1 minus 1 divided by 1 plus e power E minus EF by kBT. So this is the base equation. Now we are going to further elaborate it for E is the range of energy level here. Therefore, it has to be replaced by EV minus E, the whole power half. And we have to Further simplify this 1 minus f of e also. Therefore, I am initially going for rewriting this equation as minus infinity to EV pi by 2 8 mh by h square the whole power 3 by 2 EV minus e power half dE, and then this is taken to the other side. For this we are solving for 1 minus f of e is 1 by 1 plus e power e minus ef by kBt. Taking LCM, we get 1 plus e power e minus ef by kBt minus 1 the whole divided by 1 plus e power e minus ef by kBt. That is, this is taken towards here, then solving, plus 1 minus 1 get cancelled off. Now E minus EF, look at the diagram. E is at the lower level, EF is at the higher level. So EF minus E is positive, but E minus EF is negative. So since E power E minus EF by kBt is very much lesser than 1, in the denominator 1 plus e power e minus ef by kBt is approximately equal to 1. Therefore, this becomes 1. So, we have only this as 1 minus f of e. So, on solving this, we get the final equation as e power e minus ef by kBt as the value for substitution of 1 minus f of e. So here I am going to substitute instead of this e power e minus ef by kBt. So this is the equation. Now taking pi by 2 8m h by h square the whole power 3 by 2 out of the integration, we get, so nh is equal to pi by 2 8 mh by h square the whole power 3 by 2 integration minus infinity to EV. We have the equation EV minus e power half, EV minus e power half, e power e minus ef by kBt into d. So we have arrived up to this equation. Now we are going for taking EV minus E is equal to x kBt, because we are dealing about the occupancy of holes in the valence band. So energy E, EV, EF, all these are unknown to us, but the usual unknown value, general unknown notation used here is x always. Therefore, EV minus E is considered as the generalized form as x kBt. Depending on how much amount of energy is consumed by these electrons, they will be crossing the forbidden energy gap and will be available in the conduction band. So then holes will be created in the valence band. So based on this only, there will be change in the x value, the difference in the energy value. So we are going for EV minus E is equal to x kBt, differentiating E with respect to x. Therefore, we get minus dE is equal to dx kBt, or dE can be replaced by minus dx kBt. So instead of this dE, we need to substitute minus dx kBt. And then EV minus E can be replaced by x kBt. And then E should be replaced by here. E should be replaced by if these two can be interchanged. Therefore, EV minus x kBt. Therefore, substituting the equation NH is equal to pi by 2 8 mH by h square the whole power 3 by 2. Instead of EV minus E, I am writing x kBt power half and then e power E minus EF. So this E should be replaced by this formula. E power E is EV minus x kBt minus EF divided by this kBt. Now dE is replaced by minus dx kBt. Now, before simplifying and consolidating the above equation, we are going for limits change because the previous expression is with energy values E. Now, this is with x. Therefore, changing the limits like what we have done in this number of electrons in the conduction band equation. Now for E, the lower limit is minus infinity and the upper limit is EV. Therefore for x, we need to find for the lower limit and upper limit. When E is in the position of, look at the diagram here, when E is in the position of EV here, then EV minus E becomes 0. So in the same way here also EV minus E is equal to x kBt. This is the formula or equation we have replaced for EV minus E. So if E is in the position of lower limit as minus infinity, now EV minus of minus infinity is equal to x kBt. What is that? We are going to derive. EV plus infinity. EV itself is a higher value and infinity is also a higher value. Therefore, it becomes infinity. Now the upper limit EV. If E is in the position of EV, previously what we have told is, then this becomes 0. Therefore, x becomes 0. So, minus infinity should be replaced by infinity for the lower limit of x into consideration, and the upper limit in the valence band EV for energy should be replaced by 0 for x is taken into consideration. So here now I am rewriting this formula or the expression pi by 2 8 mH by h square the whole power 3 by 2 x power half. Here we have kBt power half and we have kBt power 1. In the same way what we have done earlier for number of electrons, we are going to rewrite this as NH is equal to pi by 2 8 mH by h square kBt power 3 by 2 is also taken out of the bracket, and then look at this, we have EV minus EF by kBt, and then the remaining e power minus x kBt by kBt is taken as separately e power n m into e power n, e power EV minus EF by kBt and then e power, I am writing the integration here, minus x kBt by kBt. We have x kBt here, therefore x power half minus dx is there. Just I am explaining here again. X power half here, and then kBt power half and kBt power 1 is taken here for 3 by 2, and then e power ev minus ef by kBt is taken before the integration sign, and then we have e power minus x kBt by kBt is taken here. Now this limit is written as the lower limit as infinity, the upper limit as 0. This negative sign is utilized for interchanging the limits. That is, the negative sign is utilized for interchanging the limit. Previously, the lower limit is infinity, the upper limit is 0. This negative sign is utilized for lower limit as 0 and upper limit as infinity. Thereby the negative sign can be taken out. Therefore NH is equal to pi by 2 8 mH kBt by h square the whole power 3 by 2 e power ev minus ef by kBt, and then here also we have kBt get cancelled off. Therefore we get x power half or root x e power minus x dx only. That negative sign is used for infinity to 0 as 0 to infinity. So again we are going to take this as or equated with pi power half by 2. So integration 0 to infinity root x e power minus x dx is equal to pi power half by 2. Therefore NH is equal to pi by 2 8 mH kBt by h square the whole power 3 by 2. Here we have pi power half by 2 e power ev minus ef by kBt. Then again we are taking pi power 1, pi power half as pi power 3 by 2 here, and then 2 and 2 as 1 by 4. Then we have NH is equal to 1 by 4 8 pi mH kBt by h square the whole power 3 by 2 e power, that is exponential of ev minus ef by kBt. This kBt is common to both ev minus ef. Then as usual this can also be written as number of holes in the valence band per unit volume of the intrinsic semiconductor as 2 into 2 pi mH kBt by h square the whole power 3 by 2 e power ev minus ef by kBt. So number of electrons in the conduction band as equation number 1, number of holes in the valence band as equation number 2. So this is NH and Ne. Now the topic is about the intrinsic carrier concentration, number of charge carriers in the intrinsic semiconductor per unit volume. So the formula being Ni square is equal to Ne into NH. Therefore substituting equation 1 or expression 1 and expression 2 here, we get Ni square is equal to 2 into 2 pi me kBt by h square the whole power 3 by 2 e power EF minus EC by KBT for NE, and then into for NH 2 into 2 pi mH KBT by H square, the whole power 3 by 2 e power EV minus EF by KBT for NH. Now consolidating the equations, we get 2 into 2 as 4, and then this 2 pi KBT by H square with power 3 by 2, 2 pi KBT by H square the whole power 3 by 2 as 2 pi KBT by H square whole power 3 by 2, that is this is with 3 by 2 into the same equation with 3 by 2, it is a power m into a power m as a power m plus m, therefore I get a power 2m, that is a power 3 by 2 plus 3 by 2, I get 6 by 2, therefore 3, taking LCM. So 3 by 2 is 1 and half, this 3 by 2 is 1 and half, therefore I'll get 3 here, and then ME power 3 by 2, MH power 3 by 2, therefore ME MH the whole power, it is a common power 3 by 2, then e power, this is e power m into e power n, that is e power m plus n, EF minus EC plus EV minus EF by KBT. So this EF minus EF get cancelled off, we have minus EV plus minus EC plus EV here. So I am writing it as 4 2 pi KBT by H square the whole power 3 ME MH the whole power 3 by 2 e power EV minus EC by KBT. This is for Ni square. So now we know that the forbidden energy gap Eg is equal to Ec minus Ev. Then what is Ev minus Ec is, I am writing it as multiplying it with minus Eg is equal to minus Ec plus Ev, which is equal to Ev minus Ec. Therefore Ev minus Ec is replaced with minus Eg here. Therefore Ni square is equal to 4 into 2 pi KBT by H square the whole power 3 MEMH the whole power 3 by 2 e power minus Eg by KBT. This is for Ni square, but we want Ni only. Therefore Ni is, I am going to take square root of this. What is square root? Square root is equal to power, for example root of x is x power half, therefore multiplying this with power half, that is power half here, here also root or power half, and then power half, and then power half. Therefore this becomes Ni is equal to root of 4 is 2, then 2 pi KBT by H square the whole power 3 by 2, 3 into 1 by 2 is 3 by 2, MEMH 3 by 2 into 1 by 2 as power 3 by 4 e power minus Eg by KBT into 1 by 2 here, therefore 2 KBT. Therefore this is the general expression to find the carrier concentration of an intrinsic semiconductor.